Hi everyone, my name is Pritam Choudhury, and in this talk I shall give an overview of our POPL paper, a graded dependent type system with a usage-aware semantics. This work was jointly done with Harley, Richard, and Stephanie. So let's begin. In our paper, we combine graded types and dependent types. During the talk, I shall discuss the three vital aspects of our paper: the why, the what, and the how. Let's start with the why. We begin with an analogy of making sandwiches. Here is a simple recipe for making a cucumber cheese sandwich. We sandwich the cucumber and cheese slices between the bread slices. But there is something that is missing from this recipe, something that recipes invariably contain. Can you guess what? The quantities. We need 2 slices of bread, 2 slices of cucumber, and 1 slice of cheese for making this sandwich. A more precise recipe would contain the quantities that we need. So the quantities give a precise description of the requirements of the ingredients. Let's consider this in the context of type theories. Here too, quantities or grades give a precise description of demand. In these two judgments, the quantities show how many copies of the variable is needed in the term. X needs just 1 copy of itself. X plus X needs 2 copies of X. Now consider this function k, which returns its first argument and ignores its second argument. Now, how do you assign the grades? Since k ignores y, so it should have grade 0, but since it returns x, it should have grade 1. Note that the grade to the right of the turnstile is always 1, so we omit that grade. Now that we have got some idea about grades, let's look at the theory behind grades. Graded type theory is based on graded modal logic, or more specifically, bounded linear logic. Graded modal logic gives a fine-grained view of modality. For example, consider the possibility of contracting COVID-19 coronavirus in different situations. If we stay at home, we are unlikely to contract it, but we are somewhat likely to contract it if we visit a store. If we go to a party, we are quite likely to contract it. Unlikely, somewhat likely, and quite likely are grades of likelihood. Now, when we specialize the modality to demand, graded modal logic becomes bounded linear logic. Bounded linear logic gives a fine-grained view of demand. For example, the function k needs 1 copy of x and 0 copy of y. So we can think of a spectrum of demand where demand is the number of copies of arguments a term needs, with 0 appearing at the bottom and omega appearing at the top. Omega is unrestricted demand. Now, in our paper, we combine graded types and dependent types. Let's also look at dependent types. It's a short overview. So dependent types are types that depend on terms. They enable rich specification of programs, and they are used extensively in theory and practice. Now that we have seen graded types and also introduced dependent types, let's see why we would want to combine them. Why graded dependent types? In 2016, Conor McBride found that graded dependent types provides a new way of combining linear and dependent types. What's more, we can track linearity and erasability using the same mechanism. Erasability is very important from a practical perspective, and linearity is also useful. This approach is very promising for several programming languages that have or are experimenting with dependent types. One of them is Haskell. It could form the basis of extending linear Haskell with dependent types. Ideas from this domain, from graded dependent type theory, are already being explored in several programming languages like Eades, Agda, Granule, etc. Now, we talked about erasability. Let's see how graded dependent types help us in erasability or erasure. Now consider this function replicate L, which takes three arguments a, n, and x, and it returns a list containing n copies of x. Now note that we don't really need a while running replicate L. Or in other words, demand of a is 0. We can know this statically by tracking demand. And we can then erase arguments whose demand is 0. This leads to speed up. Now this is a practical use of graded dependent types. Let us look at a more theoretical use. Graded dependent types help us prove some free theorems syntactically. General parametricity theorems are difficult to prove, and especially difficult when we have non-terminating dependent language. But in their absence, graded dependent types can help us prove some free theorems syntactically. For example, we can show that if a term T has bottom type, then TA for a closed type A diverges. We can also show that a term T of the polymorphic identity type, when supplied with arguments, either diverges or is essentially the same as the polymorphic identity function. Now that we have seen some uses of graded dependent types, let us see what they are in more detail. Our goal is graded dependent types, but we start with simple types, graded simple types. What do we need for this? We need grades. We saw natural numbers as grades. In fact, grades can be generalized. They can be drawn from any arbitrary semiring. But for this talk, we restrict ourselves to natural number grades only. So grades are natural numbers with addition and multiplication defined in the usual way. Our terms are almost the same except that we have a grade on the lambda. Similarly, for types, we have a grade on the domain. Our contexts are also graded, as we saw before. Now this is the grammar. Let us look at some typing rules. First, the variable rule. So we have x. X needs one copy of x. We don't need any other variable here. So they appear at grade 0. Now the lambda rule. The lambda term needs context gamma and also q copies of its argument x. So the body of the lambda b needs gamma and q copies of x. So the function that k that we saw can be assigned this type, and k can be written in this way. Now let us look at the application rule. It is somewhat complex. It has 3 judgments in its premise. The third judgment is new. What this means is that the context gamma 1 and gamma 2 without the grades are the same. Now let us try to understand this rule. Here B needs gamma 1 and q copies of its argument. A, which is B's 2B argument, needs gamma 2. So q copies of A needs q gamma 2. Hence B needs gamma 1 plus q. Hence BA needs gamma 1 plus q gamma 2. Now we can see that this judgment that we saw earlier can be derived using the app rule. So with this introduction to a graded simple calculus, let's try to move to dependent types. Now consider the replicate example again. The definition is the same, but the type is more precise. Instead of a list, we now return a vector whose length is equal to the input natural number argument. Now, replicate V uses n in 2 different ways. One is to compute the output vector, where n is used as a counter during runtime, and the other is to enforce the invariant that the length of the output vector is equal to the input natural number argument. The first use is a physical use. We can think of n as a signal flowing through the circuitry as we compute the output vector. The second is more of a virtual use. N is there to enforce a constraint. So with these 2 uses of n, uses of different natures, how do we count the demand of n? Let's see. One answer may be that we just count the physical uses because virtual uses do not ever matter. Then demand of n is 1. Another answer may be that we count both physical and virtual uses together. So demand of n is 1, 1. A third answer may be that we count both physical and virtual uses, but in separate contexts. So demand of n in replicate V, A, and X is 1, and demand of n in vec A n is also 1. This is the approach we follow when combining graded types and dependent types. The other 2 approaches have also been explored. The first one by Bob Atke, and the second one most probably in an ESOP paper that is to appear. Now that we have 3 approaches to counting demand in a dependent language, a natural question to ask is, how do they compare? So let's first look at count physical uses only. Bob-Atkins approach. This leads to two subsystems, one that is demand aware and the other that is demand agnostic. Terms live in the demand aware world, types live in the demand agnostic world. So this results in some non-uniformity. The second approach, where we count both physical and virtual uses together, this leads to some complexity. Our approach of counting both physical and virtual uses, but in separate contexts, results in a single demand-aware system. This uniformity leads to simplicity. Our typing rules in particular are simpler. Now that we have seen the what of our paper, let's move to the how of our paper. We have this language, GRAD, that combines graded types and dependent types. Our principle is that we track demands in both terms and types, but in separate contexts. The variable rule makes this principle amply clear. So the premise has a type A whose demand is gamma. It is tracked in the judgment gamma A type. The conclusion has X whose demand is one copy of X. It is tracked in the conclusion judgment. Now note that the demands of the type are zeroed out. The demands of the type gamma are zeroed out, that is, gamma is multiplied by 0 when considering the demands of the term X. With this understanding of the demand tracking principle, let's look at some typing rules. We have pi types, sigma types, and sums. The lambda rule is similar to its simpler version, but instead of an arrow, we have a pi here. The app rule is also similar to its simpler version. Now, with these rules, we can type this polymorphic identity function with this type. Note that ID does not use capital X, does not use the type argument. So X appears at grade 0. Now let us look at some meta-theoretic properties. We have the usual meta-theoretic properties. We have regularity. Regularity says that if a term is well typed, then its type is also well typed. The demands of the term and the type may be different, but the underlying context, gamma and gamma prime, without the grades are the same. Then, with a standard operational semantics, we have the preservation lemma and also progress lemma. We have formalized these results in Coq and they are available online. Now with type soundness in place, let us ponder about demand soundness. Is our system also demand sound? The standard operational semantics does not track usage. For example, in the beta rule, we should substitute only Q occurrences of the bound variable. But the rule does not even look at Q. So how can we ensure that demands are tracked correctly by our type system? We need a semantics that enforces fair usage, that substitutes according to the grades. A semantics that would substitute only q occurrences of the bound variable in this beta rule. Now, for this, we need a fine control on substitution. And we use graded heaps for this purpose. We load substitutions with their grades into the heap and then substitute one occurrence at a time. For example, consider this term. We load the substitution with grade 2 into the heap. Then we substitute the variables one by one. Substitute the variable x one at a time. Note that as we substitute x, we decrement the grade in the heap. This means that we may hit 0 at some point. Then we get stuck. For example, consider this term. It gets stuck because we have an x in the term, but we cannot use x since its grade is 0 in the heap. So what heaps do is they enforce a fairness principle. We can use no more resources than what we are entitled to. Now let us look back at soundness again. Demand soundness. Our heaps are ordered lists of graded assignments. The reduction relation takes a heap H and a term A which steps to A prime. H prime is the leftover heap. Let's look at the rules. In the variable rule, we look up x, and since we have used x once, we decrement the grade by 1. The app left rule is standard. The beta rule loads the substitution with its grade into the heap. Now with these rules, let us consider soundness. Our type system tracks demand statically. Our heap semantics enforces fair usage. So in simple terms, soundness would mean that well-typed terms do not run out of resources. Let's make this statement precise. So soundness is for a term B, if a heap H supplies resources judged to meet the demands of B as accounted by the type system, then the evaluation of B starting with heap H does not get stuck. This would mean that the type system tracks demands correctly because evaluation of B does not get stuck. Now let us formalize this statement. But before that, we have a clause, judged to meet the demands of B. How do we express this? Now we know the demands of B from its context. So a heap meets the demands of B means the heap is compatible with the context. H heap is compatible with gamma context means heap H meets the demands of any term type checked in context gamma. So the formal statement now, if H is compatible with gamma and B is well typed in context gamma, then B is a value or B takes a step to B prime such that B prime is well typed in context gamma prime and the new context gamma prime and the new heap H prime are compatible. Note that B prime has a new context gamma prime. This is because B prime may have used some resources from H. So B prime may have lesser demands. So that's why the context may change. Let's look at an example to understand this. We have this term which is well typed. This is not a value, so it takes a step, and the new term x plus x is also well typed, and the new heap and new context are compatible. Now we can use the soundness theorem again, because we have a well typed term and a heap that is compatible. So again, this takes a step, and the new term is well typed, and also the new heap and new context are compatible. Note that x plus x has used one resource from the heap and is now 42 plus x. X plus x needs 2 copies of x, but 42 plus x needs just 1 copy of x. Now we can apply this theorem again and again until we reach a value. Now let us look at a practical example of the soundness theorem. Let's use it to derive a free theorem. The free theorem we want to derive is, if T is a term of empty type, then for a closed type A, the term TA diverges. Let's go through the proof. So either T diverges or T reduces to a value V. Since T has type that has a grade 0 on the pi, the grade on the lambda must also be 0. Now, if T diverges, then TA diverges. Otherwise, let A1 be an arrow type and A2 be a product type. We show that TA1 and TA2 both diverge. Now, T reduces to a value that has a grade 0 on the lambda. So, TA1 and TA2 will step to T prime, and the heaps will contain A1 and A2 but with grade 0 in both cases. Now 0 graded assignments cannot be used. So T prime behaves the same in both the heaps. Now if T prime terminates at value V prime, then V prime should have both an arrow type and a product type. That means V prime should be a lambda and a pair at the same time. But this is impossible. So TA1 and TA2 both diverge. Hence TA also diverges. Now after this free theorem, let's look at some other applications of soundness theorem. We can show that erasure of 0 graded arguments is safe. We can also show that in-place update of 1 graded variables is safe. We can also prove the standard type soundness theorem as a corollary of the heap soundness theorem. And we can also prove some free theorems syntactically. How far can we push this technique? This is left for future work. Now that we have seen the why, what and how of our paper, let's summarize. So what did we do? We designed a language GRAD that has pi types, sigma types and sums. It tracks demands of both terms and types, but in separate contexts. The approach is simple and uniform. It has a usage-aware operational semantics. useful theorems follow from soundness with respect to this semantics? So this is the why, what and how. But why GRAD? It's because it combines linear and dependent types in a simple and uniform manner. It handles erasability and linearity using the same mechanism. It can provide a basis for extending linear Haskell with dependent types. And the type system may also be useful for other programming languages that are exploring dependent types like Agda, Eades, Granule. With this, I conclude my talk, but invite you to read our paper. Thanks a lot for your attention.